So as I mentioned in the previous slides, what ANOVA does is it compares the variability between groups to the variability within groups. And so let's talk about each of these different types of variability and why there might be differences in each of them. So there are two possible explanations for why there might be differences between the groups that we've studied. So again, between groups would be the differences in aggression levels for the people in the cold room versus average room versus hot room. So those people might be different from each other because there is an actual treatment effect. So this is what we might hope would be the case in our research, is we are hoping in our research that when we're manipulating something, that manipulation is actually working, in that it is affecting the outcome in the ways that we're expecting it to. So maybe we're going to expect that, the hotter rooms might lead to more aggressive behavior. So if indeed it is the actual room temperature that's causing the differences between the hot versus average versus cold rooms, that would be due to the treatment effect. Again, the treatment being the room temperature. So the possible difference between the groups could be due to the fact that they're experiencing these three different conditions. So ideally, that is what would cause the differences between our groups that we're testing. However, it's always the case that the differences that we're observing could just be due to chance alone. So always remember that within statistics, the fact that we're using samples is always going to have the issues of sampling error, which are, just the facts that we have different people in each of our samples. It just might lead them to already have different levels of aggressive behavior. So those are differences due to chance that we can't really explain. But these chance differences still exist between our groups. So we have different people in these different groups. Those different people are likely to have different levels of aggression before they even came into our study. So those are chance differences that might exist between our different groups. And so the source of these chance differences can be due to a couple of different things. One of the primary sources of chance differences are those individual differences. Like I was just talking about, different people might start out just being more aggressive or less aggressive. That's an example of an individual difference. It's just the ways in which we're different from each other. So different people have different levels of aggression in general. So you could think about individual differences as being personality level kinds of things. So just the ways in which we're different from each other. Just before we even get measured in the study, we have these individual differences. Another potential source of chance differences might be due to experimental error. Let's say that the experimenter who was running the experiment in the cold room had a really bad day and was being really grumpy. This introduces another issue within our study that might lead to some error in our measurements. So if your experimenter was really grumpy, then that might make your responses more aggressive or less aggressive. So those are potential issues that might lead to just these differences that we observe due to chance alone, rather than what we're hoping for, which is those differences due to our actual treatment. So the whole reason why we measure our within group variance is because it gives us an estimate of how much difference we should expect just due to chance alone. So the within group variance, so the ways in which all the people in the hot room differ from each other, that gives us an idea of how much we should expect to have differences between people just due to these chance differences. So again, the chance differences could be related to individual differences or potential experimental errors. Anything that you're essentially not studying could be a source of those differences that are just due to chance or not due to what you're actually trying to test. So again, the within group variance gives us a measure of how much of those differences we should expect just by chance, just due to sampling error and these other issues. So when we're thinking about the F ratio, in general, the structure of the F ratio is looking at the variability between our different groups. So again, that would be how does the cold group compare to the average group compare to the hot group. So it looks at the variability between those groups and it compares it to the variability within each group. So how do the hot groups differ from each other? How do the average people differ from each other? And then how do the cold people differ from each other? Another way to word that would be the variability between groups is composed of both the treatment effect and those differences due to chance. Again, our measure of the variability within groups is our measurement of how much difference we should expect just due to chance alone. The main reason I bring this up is because it helps us to understand what the F distribution ultimately looks like. So if we think about this in terms of the null hypothesis, which the null hypothesis is always going to say that there's no effect on our treatment. So if our treatment is not effective at all and this treatment effect is 0, so if our treatment was not effective and there's really no difference between the levels of aggression from the cold room versus average room versus hot room, if there's really no treatment effect, then what we would be left with is just this measurement of differences due to chance. And that measurement would be between groups, and also we would have the measurement of the differences due to chance that would be within groups. So when thinking about if we were to divide something by itself, so dividing differences due to chance by differences due to chance, we're dividing the same thing by itself. And what that leaves us with is when the treatment effect is 0, so we have, again, just going back to look at that differences due to chance over differences due to chance, if that treatment is 0, then what we would expect is we would expect our F ratio to be 1. So when there is no effect of the treatment, so the room temperature has no effect on aggression levels, we would expect our F ratio to be equal to 1. This is different from what we would expect in the t-test. So recall that we expected when the treatment effect was 0, or when there was no effect, we would expect our t to be equal to 0. So it's different with the F ratio in that when there is no effectiveness of the treatment, we actually expect our F ratio to be equal to 1. We'll talk about the other ways in which the F distribution changes, but that's one of the big things that changes from F and T is that when there's no treatment effect, we expect F to be 1. In this case, if we had an F ratio of 1, we would conclude that the treatment did not have a significant effect. So just like in the previous chapters, we've talked about how if there is no effect of the treatment, we make that conclusion that this treatment did not have a significant effect. So since we're always testing the null hypothesis, which is predicting that there's no effect, the mean of our F distribution that we're going to be working with is always going to be equal to 1. So again, the F ratio is different from the T ratio or the t-test. So F is a completely different distribution. It's also a completely different statistic. So it has a lot of different characteristics than what T had. So one of these major differences is first that the mean of the distribution, when there is no effect of the treatment, the mean is equal to 1, whereas in T it was equal to 0. So let's talk about some of the other ways in which the F distribution is different. So since our F is a ratio of two different measures of variance, this means that our values for f are always going to be positive. So they should always, always, always be positive. And the reason that I know that is because remember that variance is calculated using the sum of squares. So if you remember all the way back to chapter 4 and also the last chapter, we talked about, the last few chapters, we've talked about calculating the sum of squares. But remember, every time we calculate the sum of squares, that always involves squaring deviation scores. So anytime we're squaring anything, the resulting value should be positive. And so after we sum up all those squared deviation scores, the sum of squares always ends up being positive. And in turn, the sum of squares divided by the degrees of freedom always ends up being positive. So the value for the variance is always going to be positive. So what that means is since f is a calculation of two variances, f will always be positive. Also, what that means is that our distribution of f is going to look very different from what our distribution of t looked like. So remember our t distribution, we had half of our values for t were below the mean of 0, so half of our t values were negative, the other half were positive. That is no longer the case with our f distribution. So with f, we are now only going to have positive values, and our distribution is going to be a positively skewed distribution. So again, the tail of that distribution is always going to be to the right in our f distribution. So also, just like t, our f distribution changes depending on our degrees of freedom. So we'll talk about that more as we continue. But you'll notice that when we're looking up our critical values for f, we're also going to need to know our degrees of freedom. So one other thing is that when we do have a really large f ratio, so if we get a big value for f, that indicates that the difference between our groups is bigger than what we would expect just due to chance alone. And so when we have a really large f ratio, that makes it more likely that we're going to make that decision to reject the null hypothesis and to say that there was a significant effect for whatever we were studying. So just to give you a graphic understanding of what the f ratio looks like, I'm going to show you just an example of what an f distribution looks like. So here we have an f distribution. So again, I mentioned on the previous slide that our f distribution, it does change depending on our degrees of freedom. And you'll notice in this example, I have 2 degrees of freedom listed here. So our f ratio is actually going to involve 2 degrees of freedom, and we're going to talk more about that in a little while. But our f ratio uses these 2 different measures of degrees of freedom. And so here's an example of what an f distribution will look like. So our f distribution will always have this general same shape where it's a positively skewed distribution, which again means that your tail is over here on the right-hand side going towards bigger values. So it's a positively skewed distribution. We have no values are below 0, right? They're always going to be positive. And notice that also our mean will be somewhere, well, the exact mean is at 1. So the mean of this distribution is at 1 because we're expecting that if our treatment has no effect, then our f ratio should be equal to 1. So that is what our f distribution will look like. So one other thing I wanted to talk about was the notation that we're going to be using in ANOVA. So here are some of the various symbols that we're going to learn about in ANOVA. So we're going to use the symbol K to indicate the number of levels our factor has. We're going to use the little n to indicate the number of scores in each condition or group. Big N is going to refer to the total number of scores in the study, and MS is just a fancy way of saying variance. So in the previous chapter, we used s squared, little s squared, to represent our variance. So now in this chapter, since we're separating variance into different components, we're going to use MS.